So, welcome back. So, today like what we have discussed about the Itoh-Tsujii inversion algorithm. So, what we will do today is that we will try to see about a corresponding hardware architecture for it. Okay? Like suppose like once we have understood the algorithm, this is a very general problem that we will encounter is that we have to now translate that algorithm into hardware. Okay? So, we have already seen a flavor of that when we discussed about the GCD algorithm, and we thought about how we can discuss into the data path and the control path. So, that was an example. So, here is a more I would say specific case where we are trying to implement a finite field circuit, which is often used in several cryptographic computations. Okay. So, to start with, right, let us so this is what we will discuss today. Like we will discuss about the hardware design of Itoh-Tsujii, and we will discuss about the performance of the hardware circuit, like how we can choose the parameters so that the performance is kept nice. Okay. So, that it is optimal in terms of its performance. So, to start with, here is a brief recap of the Quad-Itoh inversion algorithm. So, we have so in this case I have set n equal to 2, but if we remember we generalized in the last class where you can make it n equal to 2, 3, 4 or whatever, and but here suppose we set n equal to 2, then this is the corresponding operation which you had to do. So, if I want to compute say an inversion in 232, then I need a I need an addition chain till 116. And therefore, right, I will essentially do this so that I finally get alpha 116. And note also in this case that we had two like in order to obtain the final inversion, we had two sub cases. Okay. In the first sub case was when n was dividing m minus 1, and in this case when you are talking about 233, then your m minus 1 is 232 and your n is 2. So, therefore, since 2 divides 232, what you just need to do is square this alpha 116. Okay. So, therefore, right, what you can essentially need to do is a final squaring to get the inverse. You do not need any other beta value computation to get the inverse, that makes it quite efficient. So, what we can do here is that if we again observe the clock cycles, just to recapitulate about that, you essentially have got L plus 1 number of clock cycles, because you have L minus 2 to do the multiplication to the L minus 2 essentially is what you do here in this table. But then you have got 2 extra multiplications at the top to calculate this pre-computation, plus the extra multiplication to do the squaring, that is 3 multiplications. So, therefore, we have got L minus 2 plus 3. So, you have got L plus 1 number of multiplications. So, that essentially is the clock cycles accounts for this clock cycle value here L plus 1, and this summation is for the remaining parts where you are doing ui minus 1, you are dividing by us. But note that now since we are doing quadding instead of squaring, we also need a corresponding architecture where we do not have a cascade of squarings, but we have a cascade of quads. Okay. So, therefore, right, I mean here is a corresponding architecture for that. So, let us take some time to understand how this architecture works. So, so again we have got a data path and we have got a control path. So, you can see that this is my control circuit denoted as control, whereas this part essentially is my data path. So, in the data path, what are the two most important operations that we need? Here we need a multiply, because we have essentially we need several multiplication operations. So, we need an optimized multiplier. Okay. We need an efficient multiplier. So, in order to do that, we can use the Karatsuba multiplier that we designed in the last class, and then we also need a quad block. So, how do you realize a quad block? So, you can observe that when you are doing quadding in GF2 arithmetic, then you are basically doing squarings followed by squarings. Okay. So, now squaring, as we discussed, right, is a linear operation in GF2 to the power of m arithmetic. Okay. So, therefore, right, you can actually realize a squaring operation by just using only XORs. You do not need any AND gates to realize that. Okay. Moreover, you can, if you want to have powers of 2, like powers of 2 means like 2 squared, 2 cube or so on, all of them can be realized as that. Okay. So, basically it is just by using XORs you can realize it. So, you can actually have a very efficient architecture for the quad block, and as we discussed, right, that the quad block essentially, right, in terms of delay is kind of equivalent to the squaring circuit. Okay. So, it is probably more optimal, or better, at least it utilizes the lookup tables more efficiently. Okay. So, now we see that we have got the multiplier, and there are two inputs to the multiplier, but the one which you will be choosing, like which one which you will say, or the data that you will be sending as an operand to the multiplier is being selected by a multiplexer. So, there are two multiplexers at the input of the multiplier, and likewise, right, for the quad block, whatever you want to compute, whatever inverse you want to compute, that data is also being selected by a multiplexer. Okay. So, you have got 3 multiplexers here. Okay. There are 2 registers at the output. So, for example, I registered the multiplier by using an mout register. Likewise, I registered a quad block and I denote it as q out. Okay. So, note that in my architecture here, I will be either using a multiplier or I will be using a quad block. Okay. So, therefore, in what essentially what I mean to say is that I will be enabling either this register or I will be enabling this register. Okay. So, therefore, at any clock cycle I will be either calculating this value here or I will be either using this value or I will be using either this value. So, you can note that the control generates an enable signal and the enable signal passes here, but it is toggled here. That means, if it is 1, then it is selecting this register, but if it is 1, then this is set at 0. Likewise, if it is 0, then this one is selected and this one is not selected. Okay. So, therefore, I am basically switching between the multiplier and the inversion. Okay. And then if I just want to take a look into my quad block, as we have seen in the square root circuit, right, what we will be having here is we will be having a cascade of quad circuits. So, here again I have got US quad circuits which I have cascaded, all of them are quads individually, and then there is a multiplexer at the output of these US stages. That means, like if the number of quadings that I want to do is less than the number of stages here US, then I can multiplex that output correspondingly. Okay. However, if the number of quadings is more, then I need to take this output, feed it back and I need to cycle it. So, I need to spend more than 1 clock cycles to do that operation. Okay. How many clock cycles? Exactly as we have seen, the number of clock cycles divided by US, and I take a seal of that. Okay. So, that gives me the approximation of the number of clock cycles that I will encounter or incur in that case. Okay. So, now once you have essentially understood the data path, so you also need to also understand that the data, right, essentially which you are computing is essentially going through transition. That means, you are essentially continuously modifying those data. Okay. So, therefore, the data that you essentially are computing on essentially is stored often in the form of a register bank. So, there is a register bank where you have registers where you are storing them. Okay. Now, the number of registers which you essentially will be having in the register bank will actually depend upon your choice of the addition chain. Okay. For example, you will see that in the addition chain, if you need to have a, like when you are calculating the alphas, right, and you need to resort or you need to take an alpha which previously was there or previously was used, then that data should be available, right, because you do not want again to compute that. Okay. Otherwise, the entire advantage will be lost. So, therefore, that old data needs to be stored in the register bank and needs to be suitably addressed to get that value. Okay. So, therefore, that depends completely upon that addition chain. Okay. So, now I would like to design the control word. So, if I want to design the control word, this is how what I do here is, so essentially, right, what I start doing is I start to like calculate the multiplications and the inversions one by one. Okay. So, if you remember, right, what we started with was calculating this alpha 1, okay, and alpha 1 was initialized to a cube. Okay. So, if you remember, right, alpha 1 was initialized to a cube. So, if you go back, right, you will see that alpha 1 was initialized to a cube, a to the power of 3. So, how can we calculate this a to the power of 3 is being elaborated here in terms of the clock cycle. So, as I said that you are basically spending 2 clock cycles here, and what I do is first I do a multiplication and then I get the corresponding result, which is a square. I again feed this back and I calculate a to the power of 3. Okay. So, what I do first is that I first need to ensure that the multiplier here gets a, that means this select line should select 0. Okay. That is why the select 1 is set to 0. What about this multiplexer? I again need to take this a. So, I again want to make this select also 0. So, this select is also set to 0. Okay. So, now I get a square. So, the select 3 and essentially does not matter. So, I have said do not cares here, okay, because so that I allow it to optimize more, because the choice of these values does not matter in terms of functionality. So, I should set them as do not cares, and then finally, right, this en is set to 1. That means, I am essentially using the result of the multiplier output. Okay. So, therefore, I get a square here, and now what I do is that I take this a square and I would like to feed that back, right, because I would like to compute a square multiplied with a. So, therefore, in the next clock cycle you will see that select 1 is still set to 0, which means select 1 being 0, it takes in A. So, therefore, this multiplier has got one of its operand as A in the next clock cycle, whereas in the next clock cycle the second multiplexer select line has been set to 2. Okay. Now, if it is set to 2, then that means I am choosing this line. Okay. So, I am choosing this line, which is nothing but the output which I have derived from here. Okay. So, therefore, I have got square, and if I am multiplying squared with A, so I am multiplying A squared with A to get A cube. Again you see that the En is being set to 1, because I am again observing this output. Okay. Now, what about alpha 2A? So, in alpha 2A, again if you observe, right, if you go back and see the computation of alpha 2A, you basically are doing this, you basically are multiplying alpha 1, okay, and you are essentially passing alpha 1 and raising it to the power of 4, and you are multiplying this with alpha 1. Okay. So, therefore, alpha 1 needs to be sent to a quad circuit, and the result needs to be multiplied with alpha 1. So, therefore, what I do in the next clock cycle is I essentially raise alpha 1 to the power of 4. Okay. So, therefore, this data I essentially get from the register bank, okay, and therefore, what I do is that I take this data and I send it to the quad block. Okay. So, now if you observe here that in this third clock cycle select 1 and select 2 are not important, because the multiplier is not working here. Rather, what is important is select 3. So, in select 3, right, I have set it to 0, which means, right, I am getting this data. So, that essentially, right, I am this is the corresponding data which I am passing it, and this data essentially is being taken from, if you observe this line is being taken from here. Okay. So, that means, right, here I had A cube calculated. So, this A cube data is directly being fed back to the quad block, okay, and once it is being fed back to the quad block, I need to observe the output in Q out. So, therefore, Q out, right, essentially is where I should get the corresponding output data. Okay. And therefore, right, I essentially also make Q select 1 and I get the corresponding result. Okay. Likewise, right, you will see that the enable signal is set to 0 here, because if the enable signal is set to 0 here, this being 0, this becomes 1. So, therefore, this becomes functional. Okay. So, in the next clock cycle, that means in the clock cycle 4, I will multiply this with A, right. So, therefore, what I have to do is I have to take this and I have to multiply this back. So, therefore, what I do here now is again I activate my select 1 and select 2 signals. So, therefore, I activate and I make both of them 1. So, that means like this is 1 as well as this is 1. So, you see that if this is 1, then that means I am getting it from the if you observe, if you trace this back, then I am getting this from here. Okay. So, I am getting this from here, and the other data I am getting from the register bank. Okay. So, therefore, I am now I am essentially multiplying, and I am getting alpha 1 to the power of 4, and I am multiplying that with alpha 1. Okay. So, essentially, right, what we have is, so if you observe, right, I mean this is clear, right. So, you have got one of the input from the register bank, whereas the second input from the multiplexer is actually taken from the output of the quad block. So, you see that if you follow this line, right, then this essentially is from the quad block. Okay. So, therefore, this is the data where you had alpha 1 to the power of 4. So, now you are multiplying this with alpha 1 to get the corresponding next output. Okay. So, exactly this is what is being done subsequently. So, you basically again need to calculate alpha 3, you need to calculate alpha 6, alpha 7 and so on, and essentially finally alpha 116. So, you can see that in alpha 116 you have to do several quaddings. So, you see that whenever this enable signal is 0, that means you are doing the corresponding quaddings. Okay. So, you are doing so many quaddings, and finally there is a multiplication. For every section you see that there are some quaddings followed by a multiplication. Okay. So, there is some squaring followed some quaddings followed by a multiplication. Okay. And finally, there has to be a squaring, that means the final result has to be squared, and this is done by a multiplier. So, therefore, again I am selecting 1, selecting 2, setting them to 2, which means I am essentially taking my prior result and I am just multiplying them. Okay. So, again the multiplier enable is high, that means I am using the result of the multiplier. So, you can observe that for all these computations I have used the multiplier. Okay. So, therefore, right, what essentially probably is the next thing that we need to think of is that once we have made a functionally correct design, is how do we analyze the performance of it. Okay. So, therefore, the first thing which is important here is to understand what is the critical path of your circuit. Okay. And you will see that most often, right, the critical path will pass through the multiplier, because the multiplier is the most costly step that you encounter. Okay. And anyway, right, there is one clock cycle or there is one event when you are doing only a multiplication. Okay. So, therefore, the critical path of your design is kind of constrained by the multiplier. Okay. So, you need a good multiplier to make your design efficient, okay, and that is why we were studying good multipliers in the previous class. But at the same time, it is also important to realize that how do you design the quad block, right, essentially should also be taken into account. So, therefore, if you make a very erratic design of the quad block, then it may happen that you make your critical path worse than that of the multiplier. So, that should be a criteria for setting the number of cascades that you are doing. Okay. So, more seriously, right, that I mean, this is a very important step, that how do you decide the number of cascades, okay, and that will essentially make your performance, make the performance or set the performance of your design. For example, if the number of the number of quad circuits, if you denote it as US, it will have an influence on the clock cycles, frequency and area requirements. You can see that if I increase the number of quad operations, increase the number of cascades, then the area requirement will increase. Okay. At the same time, right, it will also reduce the number of clock cycles. But if you decrease it, then the number of clock cycles will increase, but the area will get reduced. Okay. So, there is a trade off. So, suppose like there is a quad circuit, like one quad circuit which will take say LP number of lookup tables, and there is a combinational delay of say TP. Okay. So, therefore, right, if I want to formalize the number of, if there are US cascades, then what is the number of lookup tables that we will be consuming? It will be just US multiplied by LP, and the delay will also be proportional to US into TP. Okay. So, as I said that since your multiplier is a very crucial block and you do not want to make the delay worse than that of the multiplier. So, you will ideally like to keep US into TP less than that of the multiplier critical path. Okay. At the same time, you do not want to make US very small, because if you make US very small, then the number of clock cycles will increase. Okay. So, therefore, the optimal way, design strategy would be probably to keep US into TP close to that of your multiplier delay, slightly less, but not more. Okay. So, this is the criteria that we followed, and if you follow this, you will see that, and here is a plot to demonstrate that if I increase the number of cascades that you are doing, that is US for example, and if you implement say the GF2 to the power of 233 on a Virtex for FPGA, this is probably how your graph will look like. Okay. On the y axis, I have plotted out the computational time of the cascaded quad block, and you will see that there is, if you make the cascade the number of cascade steps very small, then also the time will be more, because you are spending more clock cycles, whereas if you make it high, then also you are spending more, there is a more delay, there is a delay. Okay, and therefore, there is an optimal point for which you get more efficient designs. Okay. And you will see that the number of cascades here, there is a region like something like 9 to 12, and we set something as 12 for example for our design. Okay. So, therefore, right, if you take this and if you want to make or see the performance, you will see that with properly chosen such design parameters, and if you plot the Quad-Itoh Tsujii inversion with the square or Itoh-Tsujii inversion algorithm, you will find out that there for all the field sizes. Okay. So, this is a kind of a plot where on the x axis you have got different field parameters. Okay. You will see that there is always a significant advantage of using the Quad-Itoh Tsujii algorithm over the square or Itoh Tsujii algorithm for LUT based FPGAs. Okay. How did we get the performance? So, normally, right, the way that we basically calculate the performance is as follows. We divide the frequency by the slices and the clock cycles. Okay. So, therefore, right, what my objective as a designer would be to improve performance, which means that I should be able to optimize my design at a higher frequency. That means the critical path of my design should be small, and also if I want to increase my performance, the number of clock cycles should be small, and if I want to improve my performance, my slice requirement should be small. So, it is a nice trade off between the number of resources that you encounter or use the number of clock cycles that you need, and also the frequency at which your design operates. Okay. So, therefore, what we plot here is that performance in terms of different field size parameters, and we see that for all the field sizes, this properly designed Quad-Itoh Tsujii algorithm should give an advantage compared to a square or Itoh Tsujii algorithm. Okay. Of course, right, you can get into more details about trying to understand why quad and why not octet for example. Okay. And essentially also decide upon the the corresponding trade offs which can encounter because of that. For time purpose, I will not go into all those trade off issues, but rather like I will redirect you to my to the textbook that we have. You will find more details about those trade-offs in the book, and you can read and try to gather them. More importantly, I will tell you about the performance that we can the inversion circuit will have on, say, a Xilinx Virtex E, because it is important as an engineer to know the figures, right. Like for example, if I ask you, like, if I take a Quad-Itoh Tsujii algorithm and if the dimension is, say, 193, what would be the order of delay which a hardware will look on, say, on a Xilinx Virtex. Okay. So here the delay is something like 0.55 microsecond. Okay. So you can compare it with probably with a software design, and you will see that there is a significant amount of advantage which you get when you resort to hardware designs. Okay. In this case, we also compare with some other competing designs and show that this design is optimal. But what is more important to understand is that for a properly chosen design and for a properly architected design, you essentially get a significant amount of improvement when you are going into a parallel hardware architecture, which is properly done. Okay. So with this, I will stop here. So what we studied essentially is a very important finite field operation in characteristic 2, which is essentially called as a finite field inverse, which is often used in several other computations. We will see them being used largely in the elliptic curve hardware that we will be studying subsequent to this. We discussed about an efficient algorithm which is called as Itoh-Tsujii inversion algorithm, which essentially relies upon Fermat's Little theorem. We also generalized it to a version where we can actually do where you can speed up your computation. You can also try to use the resources in the FPGA much more efficiently. And finally, we also discussed about a hardware design of the finite field inversion algorithm and discussed about the performance issues, like how do you choose the parameters so that you get an optimal performance of your hardware. Okay. So thank you for your time, and we will continue our discussions in the next class.